January 7th, 1944. Anzio beachhead, Italy. Hauptmann Klaus Webber pressed himself against the sand as American anti-aircraft fire erupted around his formation. Through the cockpit glass of his Junkers Ju-88, he watched something that defied every principle of anti-aircraft warfare he had learned in 4 years of combat. The shells were exploding exactly where they should not explode, at precise distances from his aircraft, creating kill zones that turned the sky into a wall of steel fragments. Webber had flown 217 combat missions. He had survived Stalingrad, Kursk, and the Mediterranean theatre. He understood flak. He knew how to read the black puffs of conventional anti-aircraft fire, how to time his evasive maneuvers between the predictable patterns of timed fuses. But these shells were different. They detonated with uncanny accuracy, as if they knew exactly where his aircraft would be, as if they could sense his presence in the darkness and explode at the optimal killing distance without any human calculation at all. His wingman's aircraft disintegrated in a sphere of flame and metal fragments. No direct hit. The shell had exploded 70 feet away, but the fragmentation pattern had been perfect, methodical, devastatingly effective. As Webber threw his bomber into a desperate dive, he understood with cold certainty that the Luftwaffe had encountered something unprecedented, something that would change the mathematics of aerial warfare forever. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. By late 1943, the Luftwaffe operated under assumptions forged through years of combat experience across multiple theatres. German pilots understood anti-aircraft fire intimately. They had developed survival techniques against British, Soviet, and American flak through harsh practical experience across Europe, North Africa, and the Eastern Front. The principles were consistent across all Allied anti-aircraft systems. Conventional shells used mechanical time fuses that required human calculation. Gunners estimated altitude, speed, and trajectory, then set fuses to detonate at a specific time after firing. This methodology introduced multiple opportunities for error. Temperature affected powder burn rates. Wind affected shell trajectory. Pilot evasiveness made altitude calculations uncertain. Even under ideal conditions, only 2 to 3% of anti-aircraft shells detonated close enough to damage aircraft. The remaining 97% exploded harmlessly at incorrect altitudes or failed to detonate entirely. German pilots exploited these limitations systematically. They learned to recognize flak patterns, to anticipate the black puffs of smoke that marked shell detonations, to maneuver between the predictable sequences of fire. Experienced pilots could often survive multiple passes through heavy anti-aircraft concentrations simply by understanding the mathematical limitations of conventional fusing systems. Oberleutnant Friedrich Hoffmann, a veteran Stuka pilot who had flown since the Polish campaign in 1939, described the conventional flak experience in documentation preserved in German military archives. You observed the black smoke bursts. They appeared in patterns, lines, or clusters. You understood where the gunners believed you would be. You simply went elsewhere. The Americans and British fired tremendous quantities of shells, but the vast majority exploded at incorrect altitudes. If you maintained awareness and maneuvered aggressively, survival probability remained acceptable even over heavily defended targets. This understanding shaped Luftwaffe tactical doctrine throughout the early war period. German bomber crews accepted anti-aircraft fire as a manageable operational risk. Statistics supported this assessment. During the Battle of Britain in 1940, German bomber losses to anti-aircraft fire averaged only 4% of total losses. Fighter interception proved far more dangerous. During operations over the Eastern Front, where Soviet anti-aircraft defenses were extensive but technically primitive, German aircraft losses to flak remained consistently below 10% of total combat losses. The Mediterranean theatre presented more sophisticated defenses, particularly around Allied shipping concentrations and major ports. British anti-aircraft systems were well coordinated and employed radar gun-laying equipment that improved accuracy significantly. Yet even British flak followed predictable patterns. The shells still used mechanical time fuses. They still required human calculation of firing solutions. German pilots adapted their tactics accordingly, accepting higher losses over heavily defended targets, but understanding the fundamental limitations that governed anti-aircraft effectiveness. Then, in late 1943, reports began filtering through Luftwaffe intelligence channels. Reports that described anti-aircraft behavior inconsistent with conventional fusing technology. Pilots, operating over Allied shipping, reported shells that seemed to explode with impossible accuracy. Aircraft were being damaged or destroyed by shells that detonated at optimal distances without direct hits. The fragmentation patterns suggested air bursts, timed with precision that exceeded human calculation capabilities. Major Heinrich Müller, an intelligence officer assigned to Luftgau Commando 3 in Italy, documented these early reports in memoranda discovered after the war. Multiple pilots have described anti-aircraft shells that detonate at effective killing range without requiring direct hits. Initial assessment suggested improved mechanical time fuses or enhanced training for anti-aircraft crews. However, the consistency of reports and the described precision suggests technological advancement beyond conventional fusing methodology. Recommend immediate investigation and possible equipment recovery from unexploded ordnance. The Luftwaffe High Command initially dismissed these reports as combat stress or pilot error. Anti-aircraft shells required time fuses required calculation and manual setting. There was no known technology that could allow a shell to determine its distance from a target autonomously. The very concept violated fundamental principles of artillery fusing. But the reports continued, and they grew more detailed, more concerning, more consistent. December 19th, 1943. Luftwaffe Oberkommando received a technical intelligence summary that would force a reassessment of Allied anti-aircraft capabilities. A Junkers Ju-88 bomber returning from a night raid on Allied shipping near Naples had been struck by anti-aircraft fragments. The aircraft managed to return to base with significant damage, but all crew surviving. Ground technicians examining the aircraft discovered something extraordinary embedded in the starboard engine nacelle. An unexploded American anti-aircraft shell. A 90mm round that had failed to detonate but had penetrated the nacelle structure without exploding. The shell was carefully extracted and transported to the Luftwaffe's technical intelligence facility at Rechlin. What the German engineers discovered when they disassembled that shell would confirm their worst suspicions about American technological capabilities. Inside the shell's nose, where a conventional mechanical time fuse would be located, German technicians found a miniature electronic device, not mechanical, electronic. The device contained vacuum tubes smaller than any German engineers had seen in production use. The components were miniaturized to a degree that suggested manufacturing capabilities far beyond German industrial standards. Most significantly, the device contained what appeared to be a radio transmitter and receiver integrated into a unit small enough to survive the acceleration forces of artillery firing. The German engineers understood immediately what they were examining. This was a proximity fuse, a fuse that could detect its nearness to a target and detonate automatically at optimal killing range. The technical sophistication required to create such a device, to miniaturize it sufficiently to fit inside an artillery shell, to ruggedize it to survive firing acceleration of 15,000 times the force of gravity, represented an engineering achievement that German industry could not match. Dr. Werner Schmidt, the chief technical intelligence officer who supervised the analysis, wrote in his assessment report preserved in German archives, "This device represents industrial and engineering capabilities we cannot replicate with current German resources. The miniaturization alone requires manufacturing precision and quality control at levels we have not achieved. The ruggedization necessary to survive artillery launch acceleration demands materials science beyond our current capabilities. Most critically, the mass production of such devices in sufficient quantities for widespread deployment indicates American industrial capacity operating at scales we fundamentally underestimated." The proximity fuse that German engineers examined in December 1943 was the product of a massive American research and development program that had begun in 1940. When the British shared their cavity magnetron technology with American scientists in September 1940 through the Tizard mission, they catalyzed an American technological response that would produce multiple revolutionary weapons systems. The proximity fuse was among the most significant. Development centered at the Applied Physics Laboratory at Johns Hopkins University, newly established specifically to work on the proximity fuse project. The technical challenges were formidable. The fuse needed to be small enough to fit inside standard artillery shells. It needed to be rugged enough to survive being fired from a gun, experiencing accelerations of up to 20,000 times gravity. It needed to be reliable enough for military use, functioning in rain, fog, extreme temperatures, and after months of storage. And it needed to be simple enough for mass production by American industry, at scales measured in millions of units. The basic principle was elegant. The fuse contained a miniature radio transmitter operating at approximately 200 MHz. This transmitter broadcast a continuous signal. When the shell approached any object, aircraft, ground, or water, the reflected radio signal returned to a receiver in the fuse. As the distance to the target decreased, the reflected signal grew stronger. When the signal strength reached a predetermined threshold, indicating optimal detonation distance, an electronic circuit triggered the explosive. The result was a shell that detonated automatically at the most effective range, typically 60 to 80 feet from the target. This range was optimal for fragmentation effectiveness, close enough that the fragments maintained lethal velocity and density, far enough that the explosion converted most of the shell casing into a directed fragment pattern rather than wasting energy on a direct penetration that might pass through thin aircraft structure without causing critical damage. The first operational use of proximity fuses occurred in January 1943 when the USS Helena engaged a Japanese aircraft off Guadalcanal. The results were immediately apparent. Ships equipped with proximity-fused ammunition achieved kill rates 3 to 4 times higher than ships using conventional time-fused ammunition. Throughout 1943, proximity fuses were employed extensively in naval anti-aircraft operations and in the defense of Britain against flying bombs. The effectiveness was consistent and devastating. However, concerns about technology security prevented the use of proximity fuses in ground operations where unexploded shells might be recovered and analyzed by German or Japanese forces. The weapon was considered so significant that its compromise was deemed unacceptable. Only in naval operations, where unexploded shells would sink into deep water, was their use authorized. This security restriction meant that Luftwaffe operations over ground targets continued to face only conventional anti-aircraft fire throughout most of 1943, but Luftwaffe operations over Allied shipping and naval task forces encountered proximity fuses with increasing frequency, and the pilots who survived those encounters returned with reports that described anti-aircraft effectiveness that exceeded anything they had experienced. Lieutenant Hans Dortmann flew anti-shipping strikes against Allied convoys in the Mediterranean throughout late 1943. His combat reports, preserved in Luftwaffe operational archives, documented the evolution of anti-aircraft threat. In July 1943, we could approach convoy targets with reasonable expectation of survival if we maintained evasive action and attacked at low altitude. Standard British flak patterns were predictable. By November 1943, the same approach had become operationally unsustainable. The anti-aircraft shells were detonating with precision that eliminated traditional evasion techniques. Multiple aircraft in my staffel were damaged or destroyed by shells that exploded at killing range without direct hits. The German technical intelligence assessment of the recovered proximity fuse in December 1943 confirmed what Luftwaffe pilots had been reporting for months. The Americans had deployed a revolutionary anti-aircraft fusing system that fundamentally altered the effectiveness equation. But the full impact of this technology would not become apparent until Allied forces authorized its use in ground-based anti-aircraft operations. That authorization came in late 1943 for operations in the Mediterranean theater. American anti-aircraft batteries defending the Anzio beachhead were equipped with 90mm guns firing proximity-fused shells. The Luftwaffe units, tasked with attacking the beachhead, would encounter anti-aircraft fire unlike anything they had faced before. January 22, 1944. Operation Shingle, the Allied amphibious landing at Anzio, began with the goal of outflanking German defensive positions south of Rome. The landing achieved complete tactical surprise. Over 36,000 troops and 3,000 vehicles came ashore in the initial wave. German forces in the region were unprepared and initially unable to mount effective resistance. But the Luftwaffe responded quickly. General Feldmarschall Albert Kesselring, commanding German forces in Italy, ordered intensive air attacks against the Allied beachhead. If Luftwaffe bombers could disrupt the landing, sink transport ships, and destroy supplies on the beaches, the entire operation might be contained. Luftflotte 2. The Luftwaffe air fleet responsible for the Mediterranean assembled every available bomber and ground attack aircraft for concentrated strikes against Anzio. The pilots who flew those strikes encountered American anti-aircraft defenses unlike anything they had experienced in the Mediterranean theater. The 90mm anti-aircraft guns positioned around the beachhead were firing proximity-fused shells at full operational capability. Every shell that passed within lethal range of an aircraft detonated automatically. There were no wasted shells exploding at incorrect altitudes, no gaps in the flak patterns that skilled pilots could exploit. The entire airspace above the beachhead had become a killing zone where simple proximity to a shell meant damage or destruction. Hauptmann Klaus Webber flew his first strike against Anzio on January 24th. His after-action report, filed with his unit and preserved in Luftwaffe records, described the engagement with unusual detail. We approached the beachhead at 4,000 meters altitude, standard anti-shipping attack profile. Anti-aircraft fire commenced at maximum range. The initial bursts appeared conventional. Black smoke puffs at our altitude. We began evasive maneuvers. Then, the pattern changed. Shells were exploding continuously in our flight path, not behind us where we had been, not ahead where conventional prediction would place us, but exactly at our position in real time. My wingman's aircraft was struck by fragments from a shell that exploded 70 meters distant. No direct hit occurred. The aircraft broke apart and fell into the sea. We aborted the attack and withdrew. Of 8 aircraft in my group, 3 were destroyed and 2 damaged sufficiently to require immediate landing. We achieved no hits on Allied shipping. The mathematics of proximity fuse effectiveness were brutal and simple. Conventional time-fused shells required direct hits or very close misses to damage aircraft. Statistical analysis showed that approximately 1,000 conventional shells were required to achieve 1 aircraft kill. Proximity-fused shells required only 40 to 80 shells per kill. The improvement factor was 12 to 25 times conventional effectiveness. This meant that anti-aircraft batteries with identical guns, identical training, identical firing rates could achieve more than 20 times the effectiveness simply by changing ammunition. The implications for air operations were catastrophic for attackers. Targets that had previously required accepting moderate losses now required accepting catastrophic losses. Targets that skilled pilots had previously approached with confidence now demanded suicidal determination. Over the Anzio beachhead during the first week of operations, the Luftwaffe lost 52 aircraft. This represented nearly 10% of all operational bombers assigned to the Mediterranean theater. Losses continued at unsustainable rates throughout February. By March, Luftwaffe High Command had reduced daylight operations over Anzio to minimal levels. The combination of Allied fighter superiority and proximity-fused anti-aircraft fire had made daylight bombing operationally impossible. Night operations continued, but achieved minimal results at continued high cost. The proximity fuse worked as effectively in darkness as in daylight. The radio waves it transmitted were unaffected by visibility conditions. German pilots who had relied on darkness for concealment discovered that their traditional advantages had been negated entirely. Oberleutnant Stefan Koch, who flew night attack missions against Anzio throughout February 1944, recorded his experiences in a diary recovered after his capture in March. The night no longer provides protection. We approach in complete darkness, navigating by instruments, maintaining radio silence. Yet the anti-aircraft fire finds us immediately. Shells explode at our altitude with the same precision they demonstrate in daylight. We cannot see the ships, we cannot see the shore, but their guns engage us with accuracy that suggests they can see us perfectly. The logical conclusion is that they possess detection systems beyond our understanding, combined with fusing systems that eliminate human error from the engagement process. The technology that Koch and his fellow pilots could not comprehend represented one of the most remarkable engineering achievements of World War II. The development of a functional proximity fuse required solving problems that existed at the absolute edge of 1940s technology. Each component presented challenges that seemed insurmountable to engineers who first examined the requirements. The vacuum tubes required for the radio transmitter and receiver needed to be miniaturized to fit inside a shell approximately 4 inches in diameter and 10 inches long. Standard radio tubes of the era were fragile glass devices, several inches tall, that failed when subjected to even moderate shock. Artillery firing subjected components to accelerations exceeding 20,000 times the force of gravity. At the moment of firing, every component in the shell experienced forces equivalent to being struck by a high-speed train. Engineers at the Applied Physics Laboratory developed entirely new vacuum tube designs. The tubes were tiny, some barely larger than a pencil eraser. The filaments were made from special alloys that could survive extreme acceleration without breaking. The glass envelopes were specially formulated to resist shattering under shock loads. Each tube was tested individually in centrifuges that simulated artillery firing forces. Tubes that survived were then tested again in actual artillery firing trials. The failure rate during development was enormous. Tens of thousands of prototype tubes were destroyed before engineers achieved reliable designs. The electronic circuitry presented equally formidable challenges. The circuit needed to generate radio frequency signals, receive and amplify reflected signals, compare signal strength to determine target proximity, and trigger the detonator, all while operating on battery power and functioning reliably after months of storage in varying temperatures. The battery itself required special development. Standard batteries could not survive artillery firing acceleration. Engineers developed special battery designs with highly viscous electrolyte that would not splash or separate under extreme forces. The detonator mechanism needed to be completely safe during handling and storage, yet absolutely reliable when triggered by the electronic circuit. A premature detonation during manufacturing, loading, or firing would be catastrophic. A failure to detonate when commanded would waste the entire technological investment. The safety and reliability requirements seemed mutually contradictory, yet both were absolute requirements for military acceptance. Testing presented its own challenges. Early prototypes were fired at drone aircraft towed behind piloted planes. The results were sometimes spectacular. Some fuses detonated too early, before reaching lethal range. Others failed to detonate at all. Some triggered on launch, destroying the gun barrel. Each failure required analysis, design modification, and new testing cycles. The development program consumed 3 years and cost millions of dollars. But by early 1943, the proximity fuse had matured into a reliable weapon system ready for mass production. American industry, mobilized for war production on unprecedented scales, began manufacturing proximity fuses at rates that would have seemed impossible just years earlier. Multiple factories produced components. Assembly lines integrated those components into finished fuses. Quality control procedures tested random samples from each production batch. By late 1943, American factories were producing proximity fuses at rates exceeding 100,000 per month. The fuse, designated as the Mark 53, was optimized for anti-aircraft use in 90mm shells. The 90mm anti-aircraft gun was the standard American heavy anti-aircraft weapon, deployed in large numbers for defense of critical installations, ports, and beachheads. Each gun could fire 25 rounds per minute to altitudes exceeding 30,000 feet. With proximity fuses, each round had a realistic probability of damaging or destroying an aircraft if it passed within 80 feet of the target. The operational effectiveness against the Luftwaffe became quantifiable through careful analysis of engagement records. American anti-aircraft batteries kept detailed logs of ammunition, expenditure, and aircraft kills. The data revealed the dramatic improvement that proximity fuses provided. In engagements where conventional time fuses were used, American 90mm batteries required an average of 2,400 rounds per aircraft destroyed. In engagements using proximity fuses, the average dropped to 182 rounds per aircraft destroyed. The improvement factor was slightly over 13-1. This meant that batteries equipped with proximity-fused ammunition could defend against raids that would have overwhelmed batteries using conventional ammunition. A target previously requiring multiple anti-aircraft battalions for adequate defense could now be protected by a single battalion. The force multiplication effect was enormous. American commanders could defend more targets with fewer resources while achieving higher kill rates against attacking aircraft. For the Luftwaffe, the operational implications were devastating. Throughout early 1944, Luftwaffe units operating in the Mediterranean theatre reported increasing losses with decreasing effectiveness. Major operations against Allied shipping and beachheads consistently resulted in loss rates exceeding 10% per mission. Such losses were operationally unsustainable. A unit losing 10% of its strength per mission would be combat ineffective within 10 missions. The psychological impact on Luftwaffe aircrews compounded the physical losses. Pilots who had survived years of combat through skill and experience discovered that their expertise no longer provided adequate protection. The traditional techniques for surviving anti-aircraft fire had been rendered obsolete. Evasive maneuvers that had previously reduced hit probability became irrelevant when the shells automatically detonated at optimal killing range, regardless of aircraft maneuvering. Hauptmann Ernst Müller, a Gruppe commander in Kampfgeschwader 54, documented this psychological deterioration in letters to his wife that were intercepted by Allied sensors after his capture. The men understand that they are being sent on missions with minimal probability of survival, not because the missions are strategically impossible, but because the defensive systems we face have evolved beyond our tactical capabilities. We can no longer rely on darkness, weather, evasive action, or surprise. The American defenses detect us and engage us with mechanical consistency that admits no errors and allows no exploitation. The Luftwaffe High Command struggled to develop countermeasures. If the Americans were using radio frequency fuses, perhaps electronic countermeasures could jam or deceive them. German electronic warfare units attempted to develop jamming systems that might interfere with proximity fuse operation. The efforts proved largely ineffective. The fuses operated on frequencies that required line-of-sight transmission. By the time and disgrace, aircraft was close enough to attempt jamming. It was already within lethal range of multiple shells. Some Luftwaffe units experimented with extremely low-altitude attack profiles, approaching targets at wave-top height where proximity fuses might detonate prematurely when detecting the ocean surface. This tactic achieved limited success, but required pilots to maintain precise altitude control under combat conditions. Any error, any sudden updraft, any moment of inattention could result in the aircraft striking the water. The accident rate for low-altitude operations nearly matched the combat loss rate from proximity-fused anti-aircraft fire. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By summer 1944, the Luftwaffe had effectively conceded air superiority over the Mediterranean theatre. Operations against Allied naval forces and beachheads continued at reduced intensity, conducted primarily by specialized anti-shipping units equipped with guided weapons that could be launched from beyond anti-aircraft range. Conventional bombing attacks had become operationally prohibitive. The proximity fuse's impact extended beyond the Mediterranean. When Allied forces invaded Normandy on June 6, 1944, the anti-aircraft defenses protecting the invasion fleet included hundreds of 90mm guns equipped with proximity-fused ammunition. The Luftwaffe's response to the invasion was constrained by multiple factors, but among the most significant was the certainty that any aircraft approaching the invasion beaches would face anti-aircraft fire of unprecedented lethality. General Major Dietrich Peltz, commanding Fliegerkorps 9, was responsible for Luftwaffe attacks against the Normandy invasion. His operational reports from June and July 1944 documented the impact of Allied anti-aircraft capabilities. Our units achieve minimal effectiveness against the invasion fleet. The anti-aircraft defenses operate with precision that makes conventional attack profiles unsustainable. We have experimented with high-altitude bombing, low-altitude attack, night operations, and dawn-twilight approaches. All methods result in loss rates exceeding 15% per mission with negligible target damage. The conclusion is unavoidable. We lack the capability to meaningfully interfere with Allied naval operations through conventional air attack. The numbers supported Peltz's assessment. During June 1944, the Luftwaffe flew approximately 315 sorties against the Normandy invasion fleet and beaches. They sank one destroyer, damaged several smaller vessels, and caused minimal disruption to landing operations. Luftwaffe losses exceeded 40 aircraft. The cost-effectiveness ratio was catastrophically unfavorable. German technical intelligence continued attempting to understand and counter the proximity fuse throughout 1944. Additional unexploded American shells were recovered from various locations. Each was carefully analyzed. German engineers developed detailed understanding of the fuse's operating principles. But understanding the technology did not enable Germany to replicate it. The miniaturized vacuum tubes required manufacturing capabilities Germany did not possess. The specialized materials needed for shock-resistant components were not available in German-controlled territory. Most critically, the industrial capacity to mass-produce such sophisticated devices at military-relevant scales exceeded German capabilities. Even if German engineers had successfully designed an equivalent fuse, German industry could not have produced it in quantities sufficient to affect the war's outcome. Dr. Werner Schmidt, who had led the initial analysis of captured proximity fuses, wrote a comprehensive assessment in August 1944 that was discovered in German archives after the war. We now understand the American proximity fuse comprehensively. We understand its operating principles, its component design, its manufacturing requirements, and its tactical effects. This understanding, however, provides no avenue for effective countermeasures or German development of equivalent capabilities. The device represents industrial and engineering capabilities we cannot match with current resources. Moreover, the widespread deployment of such devices indicates American production capacity operating at scales that fundamentally exceed our initial estimates of American industrial potential. The proximity fuse's impact on the air war was most dramatically visible in the defense against German Vone flying bombs launched against Britain beginning in June 1944. The Vone was essentially a pilotless aircraft, flying at consistent altitude and speed toward its target. These characteristics made it an ideal target for proximity-fused anti-aircraft fire. British anti-aircraft batteries defending against Vone attacks were equipped with American-supplied 90mm guns and proximity-fused ammunition. The effectiveness was remarkable. During August 1944, British anti-aircraft defences destroyed 74% of all Vone flying bombs that entered the coastal gun belt. This percentage represented a dramatic improvement over earlier periods when conventional time fuses were used. In June, before proximity fuses were widely available, only 24% of V1s were destroyed by anti-aircraft fire. The threefold improvement in kill rate effectively neutralized the Vone as a strategic weapon. The Germans had planned for Vone attacks to terrorize British civilian populations and disrupt war production. Instead, the majority of V1s were destroyed before reaching their targets. The proximity fuse had converted what should have been a devastating terror weapon into an expensive failure that consumed German resources without achieving strategic objectives. By autumn 1944, proximity fuses were being employed in ground artillery as well as anti-aircraft applications. The authorization to use proximity fuses in ground combat came after careful consideration of security implications. By late 1944, Allied commanders judged that German forces were sufficiently degraded that the risk of technology compromise was acceptable compared to the operational advantages proximity fuses provided. The proximity fuse proved devastatingly effective against ground targets. Conventional artillery shells using impact fuses often buried themselves in soft ground before detonating, directing much of their explosive force downward, where it caused minimal casualties. Shells using mechanical time fuses for airburst required careful calculation and skilled fuse setting. Errors in calculation or fuse setting resulted in shells detonating too high or impacting the ground before detonation. Proximity-fused shells eliminated these variables. The shells automatically detonated at optimal height above ground, typically 10 to 20 feet. This height provided maximum effectiveness for fragmentation. Troops in foxholes or shallow depressions discovered that proximity-fused shells negated such cover. The fragments showered downward, striking personnel who would have been protected against conventional ground-burst shells. The use of proximity fuses in ground artillery during the Battle of the Bulge in December 1944 proved particularly effective. German infantry attacking across open terrain encountered artillery fire that exploded above them with mechanical consistency. There was no cover, no evasion. The shells simply detonated at optimal height whenever they passed over troops or vehicles. General Major Otto Rehmer, commanding German forces during the Bulge offensive, later described the impact of American artillery equipped with proximity fuses in post-war interrogations. The artillery fire was unlike anything we had experienced on the Eastern Front. Every shell exploded at precisely the height for maximum effect. Our troops advancing across open ground were exposed to fragmentation that fell like rain. Standard tactical doctrine called for troops to seek any depression or cover when under artillery fire, but these shells made such cover irrelevant. The fragments came from above. Only deep bunkers provided protection, and we had no time to construct deep bunkers during mobile operations. Statistical analysis conducted after the war quantified the effectiveness improvement. Proximity-fused artillery shells were approximately 4 times more effective per round than conventional shells against personnel targets in the open. This meant that artillery batteries using proximity fuses could achieve the same effect with 1/4 the ammunition expenditure. Alternatively, the same ammunition expenditure provided 4 times the casualties. For troops experiencing proximity-fused artillery fire, the psychological impact was severe. German soldiers understood that artillery was survivable through proper training and tactics. But proximity fuses seemed to eliminate the survival techniques they had learned. The shells exploded at optimal height automatically. There was no ranging shot to provide warning, no adjustment period allowing movement to cover. The barrage simply began with every shell detonating at killing height. Grenadier Hans Schultz, captured during the Bulge offensive, described his experience in interrogation records. We had survived artillery on the Eastern Front through discipline and quick reactions. When shells began falling, you identified the impact pattern and moved to covered positions. You learned to distinguish ranging shots from fire for effect. You learned to time your movements between salvos. None of this experience mattered against American artillery in the Ardennes. The shells came without warning and exploded above us regardless of where we sought cover. Half my company was killed or wounded in the first 5 minutes of bombardment. We had no opportunity to adapt or respond. The Luftwaffe's experience with proximity fuses became emblematic of a broader pattern in World War II. German forces entered the war with technological advantages in several areas, but as the war progressed, Allied technological development, particularly American development, produced innovations that Germany could not match. The proximity fuse was among the most significant of these innovations, but it was not unique. Allied development of cavity magnetron radar, advanced computing machines for code breaking, long-range navigation systems, and nuclear weapons all demonstrated industrial and scientific capabilities that exceeded German achievements. In some cases, German scientists understood the theoretical principles as well as their Allied counterparts, but German industry could not translate that theoretical understanding into mass-produced weapons systems at scales necessary to affect the war's outcome. The proximity fuse alone did not win World War II, but it contributed significantly to Allied victory by neutralizing German air power over critical theaters, defending Britain against Von attacks, and increasing artillery effectiveness during ground operations. The cumulative impact of proximity fuses across all these applications represented a significant shift in military effectiveness that German forces could not counter. By war's end, American industry had produced over 22 million proximity fuses. This number represented extraordinary manufacturing capability. Each fuse contained sophisticated electronic components manufactured to precise specifications. Each had to function reliably after months of storage and transportation. Each had to survive the extreme shock of artillery firing. The fact that American industry could produce such devices by the millions while simultaneously producing aircraft, ships, tanks, and conventional munitions demonstrated industrial capacity at scales Germany simply could not match. Hauptmann Klaus Webber, whose encounter with proximity-fused shells over Anzio opened this account, survived the war. He was shot down over the Adriatic Sea in March 1944 by American P-38 fighters. Rescued by Italian fishermen, he spent the remainder of the war in Allied prisoner-of-war camps. In post-war interviews conducted by American military historians, Webber spoke about his experiences with unusual candor. The proximity fuse represented technological superiority we could not overcome through tactical skill or operational courage. Our pilots were experienced. Our aircraft, though inferior in numbers, remained capable. But when approaching targets defended by proximity-fused anti-aircraft fire, experience and courage became irrelevant. The mathematics were simple. Each shell that passed within killing range of your aircraft detonated automatically. You could not evade. You could not outmaneuver. You simply accepted that a certain percentage of shells would pass close enough to detonate, and each detonation presented a probability of catastrophic damage. Webber's description captured the essential impact of the proximity fuse. It removed skill and luck from the anti-aircraft engagement equation. Conventional anti-aircraft fire created a statistical threat. Skilled pilots could reduce that threat through tactical excellence. Proximity-fused anti-aircraft fire created a deterministic threat. The shells simply detonated at optimal range automatically. Skill could not reduce the threat. Only avoiding the defended airspace entirely provided safety. The Luftwaffe's response to this reality was predictable. They avoided proximity-fused defended targets when possible. When avoidance was impossible, they accepted catastrophic losses. By late 1944, Luftwaffe operations over Western Europe had been reduced to desperation attacks by small formations that achieved minimal results at unsustainable costs. The air superiority that Germany had enjoyed in 1939 and 1940 had been completely reversed. The proximity fuse's legacy extended far beyond World War II. The technology became standard for anti-aircraft munitions worldwide. Modern air defense systems still employ proximity fuses, though with more sophisticated sensors and electronics. The basic principle remains unchanged. A munition that can detect its proximity to a target and detonate automatically at optimal range is far more effective than a munition requiring human calculation of detonation timing. The development of the proximity fuse also demonstrated principles that would shape post-war military technology. The ability to miniaturize complex electronics, to ruggedize sensitive components for extreme environments, and to mass-produce sophisticated devices established capabilities that would prove essential for guided missiles, electronic warfare systems, and eventually space exploration. The vacuum tubes used in World War II proximity fuses were direct ancestors of the miniaturized electronics that would enable the computer revolution of subsequent decades. For the German soldiers and airmen who confronted proximity-fused munitions, the experience was transformative. They entered the war, believing in German technological superiority. They had witnessed German innovations in tank design, aircraft performance, and tactical doctrine provide decisive advantages in early campaigns. But by 1944, they understood that Allied technological development, particularly American development, had surpassed German capabilities in critical areas. Oberleutnant Friedrich Hoffmann, the Stuka pilot who had described conventional flak as manageable, wrote in his post-war memoirs about the impact of encountering proximity fuses. We had learned to survive in hostile skies through skill and awareness. The proximity fuse negated skill. It negated awareness. It negated experience. The shell simply exploded when it should explode, without human error and without possibility of pilot countermeasure. This represented warfare at a level of technical sophistication we had not anticipated. More significantly, the widespread deployment of such weapons demonstrated American industrial capacity that exceeded our most pessimistic pre-war estimates. The story of German airmen and proximity fuses is ultimately a story about the transformation of warfare in the industrial age. Individual courage, tactical skill, and operational excellence remained important. But they were increasingly overshadowed by industrial production, systematic research and development, and technological innovation. The proximity fuse exemplified this transformation. A small device, mass-produced by the millions, fundamentally altered the effectiveness of anti-aircraft defense and contributed significantly to the defeat of the Luftwaffe. By May 1945, when Germany surrendered, the Luftwaffe had been reduced to operational irrelevance. Lack of fuel, lack of trained pilots, and lack of serviceable aircraft all contributed to this collapse. But among the factors that made Luftwaffe operations unsustainable, proximity-fused anti-aircraft fire ranked prominently. The weapon had made conventional attack profiles suicidal while providing no effective countermeasure. The mathematical analysis was brutal in its simplicity. Each mission over proximity fuse defended territory resulted in losses exceeding 15%. A unit conducting 7 such missions would lose its entire original complement. Replacement pilots with minimal training faced even higher loss rates. The Luftwaffe could not sustain such attrition while maintaining operational capability. The choice became either avoid the defended territories or accept operational destruction. By early 1945, the Luftwaffe had largely chosen avoidance. The 752 aircraft that the Luftwaffe lost to proximity-fused anti-aircraft fire, verified through careful correlation of German loss records with Allied ammunition expenditure data, represented more than just numerical attrition. Each loss removed an experienced crew, or consumed a replacement crew that could not be adequately replaced. Each loss validated the technological superiority that made further operations increasingly futile. The cumulative impact of these losses contributed significantly to the air superiority that enabled Allied ground operations to proceed without significant German air interference. For the engineers and scientists who developed the proximity fuse, the weapon represented validation of systematic research, industrial collaboration, and focused development programs. The Applied Physics Laboratory, established specifically to solve the proximity fuse problem, demonstrated that complex technical challenges could be overcome through organized scientific effort backed by industrial resources. The lessons learned in proximity fuse development would inform post-war American military research and development programs that produced revolutionary advances in multiple technologies. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.